Hello. Now we're going to look at how to prove a theorem, in this case theorem 6.3 from section 6.3 on extending the table. The theorem we're going to prove is that the transform of t times some other function is equal to the negative derivative in the frequency domain of the transformed solution capital F of little f. Now, in terms of how we use this transformation, there are a couple of different ways. If we were to invert both sides of this equation, this is the same statement as the inverse of the derivative the derivative of a function is equal to a negative t times f of t. We saw an example before on certain forms where the function was shifted that we could factor out an exponential. That's where we had underdamped equations. Now we're looking at when a transformed function is actually the derivative of another transformed function, and that allows us to pull a negative t out of our original function. Remember that capital F is the transformation of little f. Okay, so the statement with the inverse transform is a little harder to prove because we don't have a definition of the inverse transformation except that it's the inverse of the original transformation. So we'll prove it in the original form here. So in our proof, we will show that one side is equal to the other. And it may feel like we should start with the transformed side and multiply by t, but that's actually more complicated than taking the derivative of capital F. Let's first look at what this capital F is. It's the integral of t going from 0 to infinity of e to the negative st times little f of t dt. That's what that capital F stands for. It's shorthand for the transformation of our little f function. We're taking the s derivative. Well, that's because after we integrate, the time goes away. But before we integrate, the s derivative is actually a partial derivative. So we're looking at taking the partial derivative in terms of s of this integral. And since we now can think of it in terms of a partial derivative, treating t as constant, we can pass this partial derivative inside the integral. So looking at this function of t that we're integrating, now as a function of s, we have a constant multiple of e to the negative t times s. So there's your exponential in s. When we take the s derivative, it spits out a negative t times e to the negative st, and we have that constant f of t still there. Right, constant in terms of s. And now we group our pieces together. We want to write this as the transformation of t times f. So our negatives cancel, and we get the transformation from t equals 0 to infinity. We want to write it as a transformation, a Laplace transformation, so we want to put the e to the negative st first, and then what's left is a t times an f of t. And so, this t times f of t is what we're transforming. Done. That's a very short proof. So, as you may have noticed so far, working with Laplace Transform is not necessarily complicated in the newness of methods or algebra to work with. We're using very basic things that we've seen before. The main difficulty, the complexity of Laplace Transform is in recognizing what the different terms mean and how to move back and forth between the shorthand notation of the transform and the full detailed integral expression for it, and working back and forth, recognizing when you have a simple transformation of a function, recognizing what that function is and how that transformation gets shifted back and forth. Okay, so there's our proof. Let's do an example. So let me introduce a new letter. I want to find g of t given capital G of s is 1 over s squared plus 6s plus 9. So let's first look at factoring the denominator here, if possible. Yeah, if we have 3 and 3, that's one option, and add them both times, we get up to 6s there. Other option was 9 and 1. That doesn't work out very well. In fact, we can write this as s plus 3 quantity squared. Quantity squared. There you go. So now we want to think of this function as a derivative of some other. So that's our g. I want to think of this as the derivative of some other function f of s. So to do so, f of s must be the integral of what's left. Using the fundamental theorem of calculus, we can write our function as the derivative of its integral. Kind of feels backwards, but it is one way to do it. So what is our function that we're integrating? That is s plus 3 to the negative 2 power ds. So we can let our u equal s plus 3, and then du equals ds. That's a very simple substitution. And we get our s plus 3 to the negative 1 power divided by negative 1 using our power rule. For u goes to the negative 1 over negative 1. We plug in s plus 3. And then there's some constant, it's true, that spits out. We don't care what it is because we're taking the derivative. And so we can ignore that constant. Essentially, in terms of ignoring it, what we're doing is we are trying to find one helper function whose derivative equals 1 over s plus 3 quantity squared. Since there are lots of possible functions that do that, we only need one of them. We can choose the simplest version. Okay, that's why we're ignoring it. And now I have the derivative of negative 1 over s plus 3. And that's my f of s, capital F of s. So I have capital G of s. The transformation I'm given is actually the derivative of another transformation. And our theorem says that if we invert the derivative of another transformation, what we get out is a minus t times the inverse of this secondary transformation. So it's saying that g of t is negative t times little f, which is the inverse of big F, negative 1 over s plus 3. Okay? Well, I can pull that negative out because it's linear. It gives me a t times 1 over, or the inverse of 1 over s plus 3. That has an a value of negative 3. So we get e to negative 3t. So you notice that this example shows off the many layers that we can have when working with Laplace transform. We started off with one transformed piece. You can think of it as a smoothie here if you want. We then analyzed that piece in terms of its components by factoring the denominator, figuring out if we needed partial fractions decomposition. We could have used partial fractions actually in this case, but instead I recognized that this is a fairly simple derivative, or I should say a fairly simple integral there, to allow me to write it as a derivative of some function. So I found a function whose derivative equals 1 over s plus 3 quantity squared. And that allows me to use my theorem 6.3 to write my inverse of this big transformation as a negative t times the inverse of a much simpler function. So these properties allow us to have multiple paths to the same solution. We could have used partial fraction decomposition. Not that bad. Certainly possible. But sometimes we can recognize a somewhat simpler or an alternate path to getting the same solution. So it's good to have these properties along the way.